So this video refers to lecture number 8, looking at friction, and it's the first video that examines this lecture. We're going to think about dry friction, free body diagrams that use friction, and solving some problems. The first thing to be aware of is there are two sorts of friction. There are static and kinetic friction. Kinetic if it's moving, and static if it's stationary. And we'll talk more about those in a moment, but on the whole, in statics, you'll be considering static friction. So friction is a force. If I pull a box, it's got a weight, it's got a contact force, so there's a weight, there's a pull, there's a normal contact force, there's going to be some friction opposing the box. We don't normally draw friction there, we normally draw it at the bottom here. Our force of friction. It's parallel to the surface that it's being pulled along, opposite in direction to the direction of motion, and he's trying to slow it down. Each pair of surfaces that rub against each other have a coefficient of friction. That coefficient of friction is given the letter mu, and you'll see a mu s or a mu k. Mu s, coefficient of static friction, mu k, coefficient of kinetic friction. As I've said, we'll deal with static friction in this. Now, in terms of static friction and kinetic friction, if I imagine a box, let me draw the graphs. I'm going to sketch the graph off slide 6. So we've got our push force, we've got our friction force, and we've got something that looks a bit like that. So here, static. This side of the right hand side of the line, dynamic or moving. If I push with a small push force, then it will push back with this amount of friction. If I push with a bigger push force, then it will push back, friction will be bigger, static friction will be bigger. So if I'm pushing against a box, say, the box will be stuck to the ground, it won't be moving. If I push with an even bigger force, it will push back with more static friction. So the frictional force that is experienced by the box pushing backwards does not have to be the maximum static friction force. However, the maximum static friction force is the most frictional force that can be exerted between those surfaces before which the object will move. If I put even more force in, then suddenly I've gone past my point of static friction, so I have to recalculate using kinetic friction what the force of friction will be, and it will be much lower, as you can see. And that's the idea there, is it's much harder to get something moving, i.e. static friction, the maximum static friction is much higher than to keep it moving. So the maximum static friction is higher than dynamic friction, typically. So two key points there. First of all, static friction is not a constant value, but the maximum static friction is the maximum frictional force before which something starts to move. Dynamic friction, typically much lower than static friction. And we can do all sorts of different things with that. We can think about if things are slipping or tipping on slopes and rolling down slopes and all sorts. The next few slides talk about how you might use that. What we'll do instead is we'll go through a couple of examples. Just picking up a couple of things before we go on to some examples though. Some things you may want to be aware of. When the block is on the verge of sliding, then your maximum frictional force is being applied. Also, when you've got the from slide 10, when you've got a block on a slope and it's got a normal force and it's got a weight going straight down and it's got an angle theta there and it's got a frictional force if it's trying to slide down the ramp, then it's got friction and it's got we have that last green arrow there yet. then we can say that the sum of the forces in the y, we're calling that x and that y, the sum of the forces in the y is going to be n minus w cos theta, and in the x is going to be mu s n, friction is coefficient of friction times the normal contact force, minus w sine theta, and we can then rearrange and say mu s equals w sine theta over w cos theta, which equals tan theta. So that's a simplified way, and that does come up in one of the practice questions, I believe. But if we look at the example on slide 14, that will then look at how we might use some of this. So we've got a crate. If I just quickly sketch it, so that should be the diagram you've got in on slide 14, and you've got a centre of gravity somewhere about there, about 1.05 metres up. In the middle of the crate, 0.45 from either side of the crate, and you know obviously your weight is acting there, so you've got 1250 newtons acting downwards there. And we've been asked for the maximum force that can be applied to the crate without it causing movement. Obviously there are two things that could happen if I push that crate. It could slip along the surface, or it could tip over. There's four things we don't know so far. There's contact force, there's a push force, there's frictional force, which I'm going to draw here, and there's a distance, and that distance is how far from the centre, I can draw that, how far from the centre of the crate in the x direction the normal force is acting. So just drawing that slightly larger, that's your centre of your crate, you've got a normal force acting, and you don't know that distance there. Okay. And what that means is you don't know if it's slipping or tipping, and we can explain that as we go through. So if we start off and we say that the sum of the forces in our x direction is equal to our push force minus our frictional force, which is mu 0.4 times n, and the sum of our forces in the y direction equals our normal force minus our weight. Oops. Then we can solve those, and we can say our push force equals 500 newtons and our normal force equals 1250 newtons. And what we can then do is we can then do a sum of the moments, and the moments are taken about a point at the centre just here, because that would be the point that it would tip about if it was to tip. So some of the moments about instantaneous centre of zero velocity, you might say, are going to be minus 500 times 1.35 plus 1250 times x equals 0. So our distance that our normal is acting along is going to be 0.54 metres. 0.54 actually puts our normal force, well, the width of the box is only 0.45, so our normal force is acting outside of the box. So because 0.45 is less than, or the width of the box is less than the distance where the normal force acts, it's not going to slip, it's going to tip over instead. So this whole scenario that we've imagined so far is that it's just slipping along as we normally would imagine if it's sat on a surface. However, because the distance of our normal contact force is greater than the width of the box from the centre to the edge, we know that it's not going to slip along like we'd normally imagine. We're going to have to do something different, and that means we're going to have to consider that it's tipping over instead. If it's tipping over instead, that will mean that our frictional force that we've assumed just here is no longer the maximum that it can be, because obviously that is the maximum frictional force that we could possibly have. So scenario 2 where it's tipping over, scenario 2, instead of not knowing x, we now imagine x is just 0.45. In other words, the normal contact force is acting exactly at that corner. So exactly at that corner is the point where it will tip. We've got our frictional force, and we've got our push force, and we've got our weight. I won't label the dimensions because they're in the previous one. So now we'll get some slightly different equations. We'll have a push force minus a frictional force, but we don't know what that frictional force is. It won't be 0.4 N, because that's the maximum static friction force, but we know it can't beat that because it's not going to slide, it's going to tip over. And in the y direction, we're going to have our contact force minus 1250 again. So we now know that P equals F and N equals 1250 as before. We can then do our sum of our moments about 0.0 again. It's going to be minus P times 1.35 plus 1250 times 0.45. 0. We can then rearrange and find P equaling 416.7 newtons, which means we also know that F equals 416.7 newtons. We also know that is less than mu n, because mu n was equal to 500. So if that's less, that means it is going to tip first. It's confirmed our theory that it's going to tip first, i.e. the friction force is not going to be enough to stop it tipping, which is what we would expect. So just to summarise what we did, we took the scenario, we assumed a maximum frictional force, this red box up here, maximum frictional force, and assumed it was sliding along, and said we don't know where the support force, the normal contact force with the surface is going to be acting as it slips along. We then calculated how far along that was going to be, and we said okay, it's going to be 0.54 metres along. We're going to put it outside of the box, which means it's not sliding along the surface as we'd normally deal with. So let's assume instead that it's tipping. If it's tipping, we assume that the normal force is acting right on the corner of the box. We now don't know our frictional force, but we know that it should be less than the maximum, which we've later worked out it is. We reform our equations of equilibrium, we reform our moments about 0.0, and we can work out the push force that's going to make it move. So hopefully that makes sense. There is now a question for you to have a go at. That question begins on slide 19. However, there is a piece of information missing before you start it. Assume the weight of a man to equal 750 newtons. Okay, that's a piece of information that's not given in the question, but you will need to answer the question. If you pause the video, have a go at the question, and then come back to the video, I'll show you how to solve it. So you should now have had a go at the group problem solving exercise beginning on slide 19 with the man pushing a dresser along, and you're looking for the magnitude of F needed to move the dresser and the coefficient of static friction between the shoes and the floor so he's not falling over. Well, if we start by considering the dresser on its own, we've got a force coming in at 30 degrees, we've got 450 newtons, and we've got a contact force, and we've got 0.25 times the contact force is our friction. So we know that it's going to slip. Actually, we don't know it's going to slip, we'll assume it's going to slip because he's pushing on the top, so it's highly unlikely to topple over when he's so much taller than it. Some of our forces in the x direction is going to equal F cos 30, that bit, minus 0.25n. Our sum of our forces in the y direction is going to equal n minus 450 minus f sine 30. We can rearrange and we can find f to equal 151.8 newtons, and we can find n to equal 525.9 newtons. We can then work on our picture of our man. So our man is going to have a force pushing back on him. And we know the magnitude of that force, but I'm going to put F for now. He's got a weight, which we said was 750 newtons. He's got a contact force, N, and he's got a frictional force. And if he's moving, as he moves forward, his feet will try and push backwards, so the friction force is going to be that way, which is going to be mu man N man. Okay, I'm putting subscript M to represent the man. So our forces in the x direction for the man are going to be the frictional force minus 151.8 cos 30, and in the y direction we're going to have the contact force of the man minus the 750, which was his weight, plus 151.8 sine 30. Rearranging those and solving simultaneously, the contact force is then 674.1 newtons, and the coefficient of friction for the man between his shoes and the floor is 0.195. And obviously that's not got any units because it's a coefficient, it's a ratio. So that concludes the first part of Lecture 8, looking at friction. There is another video on Lecture 8 which is looking at wedges and belts, and that's video 8 number 2, but this is that concludes video 8.1.